Hello, everyone. I wanted to make a quick video to help you with a couple of things that we didn't get to in section 2.4. Just to refresh your memory, 2.4 is all about continuity. Now, this is separate from limits, right? It's not exactly the same as limits, but we do need limits to figure out how to figure out if a graph is continuous at a certain point. So we need limits to find continuity, but limits and continuity are two separate ideas. So I want to make sure that you're clear in your mind, because when we were doing limits, we made very clear that the limit doesn't care whether there's actually a point at C, right? The limit will still exist even if there's a hole there. But continuity very much cares about holes. And where those y values are, and if there are missing y values. Continuity very much cares about that, but limits don't. I think that's going to be the most confusing thing when you're separating these out in your mind. All right, so continuity, to prove that a function is continuous at a point, we need to prove these three things. This is our continuity checklist. First thing, you have to show that your y value exists. Second, you have to show that the limit as x approaches c of your function, two-sided, that limit exists. And the last thing is, assuming both of those things exist, the limit as you approach c from both sides and the y value have to be the same there. If they don't match, you're not continuous. So that's continuity. And we talked about different types of discontinuities. And specifically, one of the ones that we talked about were piecewise functions, right? So piecewise functions, the discontinuities that can happen there is a jump discontinuity. A jump discontinuity happens when your two-sided limit doesn't exist. So basically, we had to check these places where our function can break, and you have to check each of those places and see whether or not the two-sided limit exists. So with that in mind, we're going to work through this example. So we want to find the value of c that makes this function g of x continuous. Okay, so we want this function to be continuous everywhere, right? But we have to make sure that it is. So where could this thing be discontinuous? Are there any places on this function where something could not be continuous? Well, there could be a jump here at this point where our functions meet, right? Like this x equals 5, this is the point where these two separate functions are going to meet. And so this is the place where a discontinuity, a jump discontinuity specifically, could happen. So we have to check x equals 5 for continuity, just like we did on this guy up here. So to check continuity, we're going to have to see whether or not we have a jump there. So to see if we have a jump, we're going to check the limit as we approach 5 from both sides. So first we'll look as we approach from the left, and then we will look as we approach 5 from the right of my function. And okay, so I need the limit as x approaches 5 from the left. We'll start with our left-sided limit. Now, to figure out how this limit's going to work, we need to look at our function. Now, our function g of x is either going to be x squared minus c if our x values are less than 5, or our function g of x is going to be 4x plus 2c if x is greater than or equal to 5. So, question is, what are our x values here? Well, we are approaching x is approaching 5 from the left. If we approach 5 from the left, our x values are going to be a little bit less than 5 because we're coming at it from the left, from numbers that are smaller than 5. So since x is less than 5, notice right here, if x is less than 5, we are going to use x squared minus c. That's what we put in place for g of x, because g of x is x squared minus c when x is less than 5. So now that we know what function we're using, now we have to do this part and find the limit as x approaches 5 from the left of x squared minus c. This is an algebraic limit. We've done this before. Your first line of defense here is to take 5, this number, and plug it in for this variable. Now, I've got two variables here, so don't panic. Just kind of do what the limit tells you to do. Plug 5 in for x. So if I'm plugging 5 in for x, I'm going to get 5 squared minus c. This is 25 minus c. I know it feels weird because there's a c in there. Don't panic. We're just going to leave it. This is the limit as x approaches 5 from the left. It's 25 minus c. That's the number that we're headed toward. Okay, now we have to do the limit from the right. Let's see what happens as x approaches 5 from the right on my function. So we are going to approach 5 from the right. And now in order to evaluate this limit, we need to figure out what g of x is going to be when we approach 5 from the right. If we're coming at 5 from the right, we're approaching from x values that are a tiny bit bigger than 5. So since x is a little bit bigger than 5, we are here, right? X is a little bit bigger than 5. I'm using this value for g of x. So I'm going to replace g of x here with 4x plus 2c because that's the function that g of x is when x is a little bit bigger than 5. Okay, so now that we have that function in there, now we have to evaluate this limit. Algebraic limits, we're going to take this value, plug it in for that variable. And so we are going to take that 5 and plug it in for the x here, and then we have plus 2c. C is just a number, we don't know what it is, but we can't plug the 5 in for it because it's not an x. So we're just going to let it be. So then when we plug that in, we get 20 plus 2c. So that's the number that we are approaching as x goes toward 5 from the right. Okay, and this is the only place where this function could have a jump discontinuity. So we're going to be continuous everywhere else. So for the whole function to be continuous, I got to make sure that we're good right here. I have to make sure that there is no jump discontinuity, which means the limit from the left and the limit from the right need to match. So these guys need to match in order for this function to be continuous. So I'm going to set them equal. So I'm going to do 25 minus c equals 20 plus 2c. And now I just have to solve this and figure out what c is. So I'm going to put all my c's on one side, anything without it on the other. You can really do either way. I'm going to add this c to both sides because I like to keep my c's positive, which means I'm going to move that 20 over here because it doesn't have a c in it. And so I'm going to get 3 c's over here. I'm going to have 5 left over here. So when I divide both sides by 5, I get c equals, divide both sides by 3, sorry. My brain is going a little faster than I want it to. 5/3, there we go. We're going to divide both sides by 3. C is 5/3. This is the value of c that will make this function continuous because my left and my right limits will be the same at this breaking point, and we will make sure that we don't have a jump discontinuity and we are continuous there. All right, so hopefully that helps you with that one. Don't panic with the c's. The limit says you plug this number in for x and let c be c. You'll solve for it in the end. All right. Hopefully that helps you with that one. That was the big one that we didn't have time for in class. We did cover if you're given a big scary algebraic function and you have to figure out where it's continuous and where it's not continuous. I have these domain rules, right? So our naturally occurring functions are continuous on their domains. So really, to figure out where a function is continuous, you just have to find its domain. That's something that you've done before. These are our domain rules. If you have a fraction, you got to make sure that the stuff on this bottom does not equal 0. If you have a root, odd roots are good. They're continuous everywhere from negative infinity to infinity. But if you have an even root, you got to make sure that the stuff under the radical is greater than or equal to 0. And if you've got a log, you got to make sure that the stuff inside your log is strictly greater than 0. Anything else is continuous from negative infinity to infinity. So all of our sines, our cosines, our exponentials, our polynomials, I'm trying to think square root, not square roots. We have a rule for that. I'm trying to think, yeah, any of our other functions, if it's not either a fraction, a root, or a log, it's continuous from negative infinity to infinity. Okay, and we just have to apply these to anything that shows up in our function. The So applying those rules is kind of the easy part. The thing that can get kind of hard about these is if you have multiple roots, putting all of these things together to figure out what your continuity sections are. And a number line helps a ton with this. We did one of these in class. So use those number lines to help you put those pieces together. The other thing that can be particularly frustrating is once you have these inequalities specifically set up, sometimes solving inequalities can get annoying and frustrating. So I just want to do a couple more examples, especially of these kinds of things to help you figure out how to solve some of those inequalities and kind of refreshing some of our algebra um, methods to figure out how to solve those inequalities, because that's something that we did back in college algebra. Okay, so I want to start here with number 3 to do a couple more examples for you. So the ln of x squared minus 4 is my function. So do I have a fraction, a root, a log? None of those, a few of those? Yes, I have a log, right? Just a log. We look like this. So I'm going to apply the log rule. Log base b, that's my ln, that's log base e. And my stuff inside the log is x squared minus 4. So the log rule says that that stuff inside my log, x squared minus 4, has to be strictly greater than 0. Okay, well, that's not so bad. Now we just have to solve this inequality. So you're going to be tempted to come at this kind of like an equation, and you're going to want to move that 4 to the other side, and you'll get here. The temptation is going to be to just take the square root of both sides and say that x is greater than 2. But the problem with that is that a lot of our functions don't necessarily preserve inequalities. If I take the square root of both sides, it's not going to preserve this inequality, and weirdo things can happen. So I can't just take the square root from here. If you have anything more than a linear inequality, right? If you have x to a power, if x is stuck inside a function in an inequality, you can't solve it directly. The way that you have to go about it is first solve the equation, and then we're going to test values around those solutions on a number line. It might be kind of rusty, but it'll probably feel familiar once we start getting into this. All right, so I'm going to solve the equality first. So if x squared is 4, I'm going to take the square root of both sides. That means x is, don't forget, plus or minus 2. So x can be 2 or x can be negative 2. Those are my solutions. That's where x squared is equal to 4, but I don't want x squared to be equal to 4. I want it to be bigger than 4. But we solved for the equality because these two values separate our number line into pieces. Each of these pieces will either be greater than 4 or less than 4 in our inequality, but we're not sure which is which, so we have to test some values. So you're just going to pick your favorite representative from each piece. Doesn't matter what representative you pick as long as it's in that piece. So what's your favorite number less than negative 2? Mine's negative 5. If you picked a different one, don't panic. Just plug yours into this inequality and we're going to see if it works. If I plug negative 5 in there, I get negative 5 squared. That's 25. Is greater than 4. Yes, that's legit. That part works. Now I'm going to pick my favorite representative between negative 2 and 2. My favorite representative is 0. If you have a different favorite representative, use yours. If I plug 0 into this equation, I get 0 squared, which is 0 is greater than 4. But that's not right. 0 is not bigger than 4, so this doesn't work. And then my last one here, if I pick something bigger than 2, my favorite representative bigger than 2 is 3. If I take 3 and plug it into this equation, 3 squared is 9. This says 9 is greater than 4, and that's legit. That's true. This part works. So the solutions to this inequality are going to be the pieces of this this number line that worked. So it's going to be everything over here and everything over here. So that's going to be from negative infinity to negative 2. Notice -2, there was not a little equal to sign. This is strictly greater than 4, so I am not going to include 2 or -2. And so these are going to be parentheses or open circles or parentheses. And so I'm going to union that with this part over here, which is everything from 2 to infinity. These are the pieces that work in this inequality. So this is the domain of this function, and thus where this function is continuous, because it is continuous everywhere on its domain. Right? That inequality is can be tough to solve. Okay. Next one. How about number 4? I have to figure out where this thing is continuous. Okay, and again, this is going to be continuous on its domain. So I'm going to go back up here. I'm going to look at my domain rules, and I'm going to say what applies to this. Do I have a fraction? Do I have a root? Do I have a log? Do I have a few things? Do I have nothing? What do we got going on? Yeah, I just have a fraction, right? There's no roots in here. There's no logs in here. I just have this fraction. So we just have to apply the fraction rule. Fraction rule says you don't care what's up here, right? This is continuous everywhere. It doesn't see that. Don't worry about that. You have to make sure that the stuff on the bottom, x squared plus 1, you have to make sure that that is not equal to 0. So we're going to solve this just like a normal equation, but with that slash through it. So x squared cannot be equal to -1. And you're going to say, ooh, I'm stuck now, right? I cannot take the square root of -1. I can't solve this. And so what that means is that there aren't solutions to this, right? X squared is never equal to -1. This is always true, right? I can't square something and get -1. I can't do that. There aren't any x values in existence that make that happen. So this doesn't have any solutions at all. So what does that mean for my domain? Does that mean there's nothing in my domain? Well, let's think about this. When we solved for x here, if we got any solutions out of here, those would have been the values that x couldn't be, because those would be the values that made my denominator 0. The fact that we didn't get any solutions out of this means that it doesn't matter what I plug in for x, this denominator will never be 0. Right? You can play with a few numbers, plug in a few x values, and after you plug in a few, you'll kind of see the pattern and you'll realize, oh yeah, that denominator is never going to be 0. I can plug in any x value I want, and that denominator will always be positive. It's actually going to be bigger than 1 all the time. And so that means my domain is -infinity to infinity. Everything works. Basically, the fact that there were no solutions here means nobody gets kicked out. Right? Because up here on the fraction rule, when we got that z could not be 3 and could not be -2, those were the two values that I had to kick out because they didn't work. We didn't find anything that didn't work. So nobody gets kicked out and everybody gets invited to the party. And that means that our domain and where we are continuous is from -infinity to infinity. Hopefully that makes sense. And so if you get to a point where like you can't solve an inequality and you get stuck, I want you to think about what that means. Sometimes when you do logs or roots, sometimes you'll get to a point where you can't solve it. So let's say I did the log rule and I got that x squared plus 1 had to be less than 0, right? I know that this inequality would be backwards, right? Well, here, okay. Sorry, let's say greater than 0. That way it's something that you could get out of a log. Okay, so let's say that we had x squared plus 1 inside a log, and the log rule says that that has to be greater than 0. Then you have to solve this now, right? Again, you'd solve what you could, and you would do x squared is greater than -1. And you would say, well, this is bigger than, this is not just an x, this is more involved. So I'm going to start by solving the equation, and then I'll put those things on a number line and test values around them. But even if you switch to the equation, you're stuck again. You can't take the square root of a -1, right? There are no solutions to this. Oh, okay. So if there are no solutions to that, does that mean there's no solutions to this inequality? Well, not necessarily. Remember, the solutions that you get from that equation are the things that you put on a number line, and they kind of cut your number line up into pieces. So what this means is that we don't have anything that cuts my number line into pieces. The number line is one solid piece. Either everything works or everything doesn't work. So how would we figure out if everything works and my domain is -infinity to infinity, or if my domain is nothing, right? If nothing works? Well, the number line is one giant piece. So you can pick a representative and test it out, just like we did before. We just don't have multiple pieces. We only have one piece. So you can pick um, your favorite representative. I'm gonna pick -5. And so if I take -5 and I plug it into my inequality, when I plug -5 in there, I get 25 plus 1 has to be greater than 0. 26 is in fact greater than 0. That's legit. -5 works, which means the entire number line, that whole piece, works. That means that this thing would be continuous from -infinity to infinity because everything worked in there, right? Does that make sense? So if you get stuck with some of these inequalities, some of these can be hard to kind of logic out and solve. So basically, I want you to solve the equation, take those values, put it on a number line, test values around it. And if you don't have any solutions, I want you to think about what that means. It just means that you don't have any representative, or you don't have anything to cut the number line into pieces. Either everything works or everything doesn't. And if you get stuck, just pick any representative, plug it in, and see if it works. Cool. So last thing that I want to do is number 6. Now, m of x equals the tangent of x. Okay, tangent. Tangent's not on my list, right? It's not a fraction or a root or a log. So that means it should be continuous everywhere, right? Hmm. Tangent we have to be careful with. So some of our trig functions that can be written as quotients or reciprocals, we have to be careful with. So tangent, cotangent, secant, and cosecant, we have to be careful with those because even though they are functions that aren't on this list as they are, technically they can be written as fractions of other functions. So tangent, right? We have a quotient identity for this from trig. Tangent can be written as, yep, sine of x over cosine of x. It's hopefully that's still in there. Our identities haven't completely left the building. So tangent is sine over cosine. It's a fraction. So I want you to just be careful with, again, these quotient and reciprocal functions in trig. Tangent, cotangent, secant, cosecant, you'll need to write them as a fraction and then go back and apply our domain rules. So now that we've rewritten it, we have a fraction and we have to apply the fraction rule to this. Fraction rule says the denominator can't be 0. So the domain of this thing is going to be everywhere where the cosine of x does not equal 0. Okay, so where is the cosine of x equal to 0? Well, you would go back to your unit circle, or you can look at a handy dandy graph of cosine of x, right? This would continue on in both directions. It's 0 here and here, which are pi over 2 and 3 pi over 2. Or you can go to your unit circle and you'll find that the x coordinate on our unit circle is 0, both at pi over 2 and 3 pi over 2. So these are the values on our unit circle that make cosine equal to 0. But again, if we want all the solutions everywhere, we have more as we keep going. I'm going to say or anything coterminal with these. Anything in the same spot on the unit circle. And so basically, we are going to be discontinuous at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on and so forth. It's going to be all our odd pi over 2s. That's where this thing is discontinuous because the bottom is 0. Tangent has vertical asymptotes there, right? We have infinite discontinuities at all of those odd multiples of pi. So this thing is going to be continuous. I'm all out of space here, so I'm just going to put an arrow here. So tangent is continuous everywhere except odd multiples of pi over 2. Okay. There's not really a great way to do that. If you really wanted to put it into interval notation, it would be really hard to do that. You would just kind of have to do a dot, 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 union negative 3 pi over 2 to negative pi over 2, union negative pi over 2 to pi over 2, union pi over 2 to 3 pi over 2, union dot, 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 right? You'd have to basically establish a pattern and then continue that pattern on with these ellipses because we're going to have infinitely many intervals and it's just not easy to write out. So if you ever have to do this, I'm totally good with whatever your brain wants to tell me, but you have to tell me that we are discontinuous at all of our odd pi over 2s. However, your brain wants to kind of put that into words for me to make that clear. All right, so hopefully that helps you with the rest of 2.4 continuity. So this is kind of a difficult concept, especially when we were still wrestling with limits. So take the time, wrestle with these concepts, figure out what the difference between continuity and limits are. They're connected, but they're different. And start wrestling with your domain rules and refigure out how to find the domains of all of our functions because our algebraic functions are continuous on their domains. And again, we know how to find types of discontinuities and make sure one thing that it's hard to test in Achieve is that if you are saying that something is continuous, you have to know how to check that. And in your notes, when you're saying that something is continuous, you should be able to check these 3 boxes. So this isn't necessarily something that we can test and Achieve, having you write all of this out. But when you do your work, if I say show something is continuous or is this continuous here, you have to show me which of these breaks down. So these, they're hard to test and Achieve specifically, but these should be in your notes. And you should be using this checklist to help you figure out if things are continuous or not continuous. All right, so I hope that helps. Happy limit and continuity-ing, and I will see you next time.